Okay, thank you very much, everybody who's coming here. Good morning to everybody. Guten Morgen, right? Radu, you can say in Romanian also. Okay, then first of all, I would like to thank Radu and people who helped him to organize this one-word seminar, because it was in the very beginning of pandemic, and in that time people were a bit, disoriented. And I think Radu's seminar was the first one, to the best of my knowledge, who was organized in such a big scale. Then in other seminars were organized as well during the 3 years, but the seminar here in Vienna was really remarkable. And then now actually the conference which also was organized by Radu and Yura, and then now it's great to see here friends and young people, new researcher, and to discuss many interesting things. Today I would like to talk about what we call semi-Newton methods in difference programming. This is joint work with Fran Aragon from University of Alicante and Pedro Perez from University of Chile. Oh, they have some other names, but the main name is Aragon and Perez, because so many Aragons and Perez, they put some kind of dash. It's Spanish stuff. Actually, Aragon, sometimes known Aragon-Artacho, and people refer to him as Artacho, or in sometimes Aragon and Artacho. But it is wrong. He is Fran Aragon, Francisco Aragon. Okay. Anyway, this is a joint work which will be published soon in mathematical programming. But here I would like to present the main issues here. Then, what we are going to consider? We consider problems of difference programming. We minimize function phi, actually here unconditional, but then we will consider constraint optimization as well, then which is represented in terms of a difference of two functions. And this class of function has been very much investigated and well known in the case where both functions g and h are convex. Such class of function is known as DC programming, difference of convex programming, and so much has been done in algorithmic developments and also in various applications of this class of function. I'm sure that most of people here are much familiar. But we consider more general framework where function g may be just C11, it means continuously differentiable with local Lifshitz gradient, and function h may be just prox regular. Prox regularity is really a broad class of functions from, say, viewpoint of second order analysis. It's the main class of functions, but otherwise it includes all good functions which we are familiar with. Of course, convex, extended real variate convex, and then different low convex, low smooth, mutables, and different kinds of situations. Then any good functions put like that. Any good function is prox regular. I'm not going to give formal definition. It can be found in any book, in particular in the book of Rockefeller and Wetz. And it has been investigated in both finite and infinite dimension. Here we are in finite dimension, which simplify many things, although something can be done in infinite dimension as well, actually doing something there. And we actually label this class of function as functions of problems of difference programming. And what is interesting here to observe that the algorithm which I would like to present and discuss, this algorithm provides new results for DC programs. When we have convex problems, we have new results, and experiments show that this algorithm, which I'm going to present, has really big advantages with respect to some other algorithm in difference programming like DCA and also a boosted version, which Frank developed before. But let me consider this full generality. Then, first of all, the name. Actually, here as I mentioned, we consider difference programming, and function may be non-smooth and non-convex. Actually, non-smooth in the second order because G is C11. It's non-smooth in the second order. And our algorithm has flavor of the second order. And then, as I mentioned, this class of functions appeared in various applications, and I will list some of the applications which we obtain application of this algorithm. Then what about the name? We actually call this regularized coderivative-based damped semi-smooth methods. And abbreviation is RCSN. Why is this so long name? Because this title emphasizes the main points which we use in this algorithm. Then it is a regularized Newton type damped methods, which Armijo rule, which we use there, and related to distance programming. And then, but instead, when we do not have convexity, we use here for function h, actually for function negative h, we use limiting subgradient, not Clark subgradient or convex subgradient will be the same, of course, but this one. And this provides some advantages. I will discuss about it. And then for function g, which is non-convex in the second order, we use generalized Hessian, or as we call second order subdifferential, which is related to the coderivative calculation. And everything will be computed. We'll provide some scheme and then computed. And then this long name emphasizes main features of this algorithm. But of course, we are going to use RCSN. And let me proceed. Our main point is second order analysis. But let me remind something from first order analysis, which we are going to use here. The basic construction is a normal cone, which is written here in the limiting form. Okay, here, well-known definition, and we consider collection of all V such that there is sequences xk, which converge to x bar, sequences of non-negative numbers, alpha k, sequences of projection here, such that this linear combination converges to V. What do we have actually? Where is it? Chop? Yeah, okay, sorry. Let's consider the simplest function. Let's consider epigraph of absolute value x. Then in this case, of course, we have normal cone of convex analysis. And, okay, and nothing else can be done. And of course, Clark normal cone, which is convex closure of this guy, is also a normal cone of convex analysis. But how about function like z, negative absolute value x? For this case, we have only two rays. Normal cone to this epigraph of negative absolute value x. Only two rays, no convexification there. And how about such set when we have just graph of absolute value x? In this case, our normal cone is like that. And these two rays. And Clark all the space. That convexification is pretty dangerous to consider graphical set. And graphical sets, they appear very often. And by the way, this example of function absolute value x is just particular example. What is known that for any for a graph of Lipschitz continuous function, any Lipschitz continuous function, or even more Lipschitzian manifolds, which include graph of monotone operators, complementarity problems, whatever we are saying, we always have such a picture that Clark is the whole space or subspace of maximum dimension. And here, of course, affect our situation. Then, in particular, this is what coderivative construction, which is defined, which is defined in this way, coderivative in terms of normal to the graph. We have exactly situation here. And of course, it's just the beginning of the game is definition. What is important calculus and computations. And we have this one, I will talk more about it. Then we define this coderivative. In the case, coderivative of any set-valued mapping. That in the case when we have, C1 function, we have a joint Jacobian. The star stands for a joint or transpose matrix Jacobian we have here. In general, this is positive homogeneous mapping, and we have calculus what is important. Then, regarding a subdifferential, schematically, for simplicity, we define in terms of normal contours the epigraph, like here. Say, in the case of this function, of course, we have the whole -1, 1, but in the case of such function, we have just -1, 1 without convex version. That's typical situation. And of course, there are many analytic representations which used for calculation, like in terms of regular Fréchet subdifferential, proximal subdifferential, epsilon subdifferential, whatever you wish. And this is just to show the idea. Then we have full calculus for this, although constructions are heavily non-convex. Now, the question is why? And the answer is because of variational principle. Here, variational technique, which is used to develop calculus and to develop various things here. In the case of Clark, we use convex analysis or convexify analysis. We use convexity of direction derivative. Here is not the case. Okay, then again, this calculus may be even better than Clark. What we miss plus-minus symmetry. You know that for Clark, for Lipschitz function, for Clark, subdifferential of f, of negative f is equal to negative subdifferential of f. In our case, we don't have this property. We need to consider symmetric subdifferential, which still is much smaller than Clark. Okay, that's what just for the taste of this stuff. Then the main construction here is second-order subdifferential or generalized Hessian, which is written there. Again, in schematic form, it is coderivative of subdifferential, derivative of derivative. In our case, first derivative is subdifferential, and derivative of set-valued mapping is coderivative. Then this construction, again, is just formal definition. We have many things behind which are used. When we have a C2 smooth function, then it is just the Hessian. Here, classical Hessian and symmetric, of course. For the case of C11 function, we have scalarization, of the gradient, and this scalarized by U. But in general, again, this is positive homogeneous mapping, and we can compute this guy. We have full calculus, but it's not enough for numerical method. We need to compute fully in terms of given data. And it has been done for many important applications, like SDP, for example, of course, nonlinear programming and all minimax problems and ice cream programming and whatever, and actually it is written in my book, which published last week. Then if you wish, you may look at this book, and there are some chapters about full calculation, calculus and calculation, various applications. We know application to variational stability there, like till stability, full stability, but that's more. Now we would like to discuss numerical technique, how to use this guy in numerical algorithms. Okay, and I would like to remind some notion from variation analysis, which most people are familiar with, and of course they can be found everywhere. This strong metric subregularity, which is kind of Lipschitzian type, but with fixed x bar, y bar, models kappa. This property is well known to be equivalent to the isolated calmness of the inverse. And also, about notion of calmness in our case, which we use is here, which Robinson called upper Lipschitzian. Here, the difference that x bar is fixed. We do not vary these points around x bar, but x is varied, but x bar is fixed. And we talk about some exact calmness bounds at infimum of this kappa here. Then again, let me remind you, strong metric regularity, it is definition when inverse function admits single-valued and Lipschitz continuous localization. That's notion which well known. You can find this in any book on variation analysis. That is new notion which may be of interest for some people, a notion which extends positive semi-definiteness. We say that set-valued mapping is a C lower definite if we have such an estimate that in a product yx greater or equal to C square norm of x for all xy from the graph. Then when C is non-negative, that we have positive semi-definites, positive definites when C is positive, but in general, C may not be positive, any real number. And that's some good examples when we can proceed in the case when we do not have positive definites. For example, when we consider any symmetric matrix Q, then the smallest eigenvalue here is, for this one, then such a function written like that is, lambda mean, smallest eigenvalue, lower definite. Then, of course, this guy may not be positive. Then also, if function is strongly convex, as everybody knows that, this quadratic shift if convex, negative quadratic shift convex, that this guy is rho lower definite. Again, rho here positive. Then we do not have, this situation in general. Then we have calculus, in particular simple calculus that when we have two mappings which are C1 and C2 lower definite, then we have sum is also a very simple result and very useful. In fact, and then we have composition, all stuff like that can be done. Now the algorithm. An algorithm in general, conceptually, it is built as the following way. We have given data, starting point, we have a global convergence, but let's fix starting point. Then we have parameter, beta from 0, 1. Then this guy, I don't remember what is the name, anyway. Put here C for a moment. We have some given time, and we have sigma, and then we proceed like that. If Wk is 0, it's stationarity, we stop. Otherwise, we proceed, and then we choose this rho k and dk direction, non-zero direction, such that we have this Newton equation, Newton inclusion. And here, the most troublesome stuff. Now, how we build this guy? We use second order subdifferential, generalized Hessian for G at dk, and we plus some, regularization, rho k dk, when dk is, we select this dk from this viewpoint. Of course, we should prove that such inclusion solvable, and it is done. Of course, we need to, this algorithm can be built. And then we proceed in such a way that we pick some tau bar k from this given interval, and then set our k equal to tau k bar. It is our step size direction, and then use Armijo rule here with this kind of modification and proceed as usual. Then our next iteration is here. Then the main point is here. Then we are going to discuss not only solvability, but performance, convergence, all stuff like that, and of course, how to calculate this guy. Because to implement this algorithm, we need to calculate. And we can do it for pretty broad class of functions, in particular for application, which appears in machine learning. I will talk about this application in some biochemistry and some other issues. Okay, then what about the performance? What could we say in general? We have this difference function, as usual, as we define, consider this Lowell set, and then we assume that G is C11. It's our standing assumption, and second order subdifferential of this function is C lower definite. C may not be positive, may be arbitrary. That's what main assumption here. Then H, as I mentioned, is prox regular, actually locally Lipschitzian, but we can overcome this, but prox regularity is the main issue here. And then we claim that this algorithm RCSN either stop in a stationary point or produce sequences which do convergence, which do converge. We have here sequences of iterates from level set, sequences of values, sequences of the subgradient, sequence of direction, and sequences of step size. Then for this one, what we have here, then for all these sequences, we can say that sequences of values monotonically decrease and converge. And if there are subsequences of iterates which are bounded, and we have these conditions, then this is tell us about the convergence, not rate of convergence, but this is estimate which is pretty useful, as everybody knows, and what we would like to get in numerical technique. Then, if subsequences converge to x bar, that x bar must be stationary point. And we have properties that value of phi at x bar is infimum of all phi at xk, where xk are iterates. That's useful property. And then, if you have isolated accumulation point, we have full convergence of the whole iterates, and x bar is a stationary point. Okay, then let me remind you this what we call semi-smooth differentiability. Semi-smooth differentiability when function is C11 and its gradient is semi-smooth. That's what people know about it much. Then what do we have in this case? Then if we assume that subsequences converge to x bar, actually the whole sequences, subsequences always converge, but because the whole sequences converge to some cluster, accumulation point x bar, and then what we have, that the sequences converge linearly. We can guarantee linear convergence rate of iterates and values and subgradients in general without any additional assumption. But if we have some additional assumption, some interplay between parameters, given parameters, and G is semi-smoothly differentiable, and H is C 1, 1, then we have superlinear convergence. Then it is we have high convergence rate under some additional assumption, but without semi-smooth differentiability, we have linear convergence rate, which actually more or less natural result because this is semi-Newton method. Semi-Newton means that we use second-order information only for function g, and we use only first-order information for function h. Then it's not fully Newton, but semi-Newton. And then we have interplay between high convergence, semi-smooth convergence, and linear convergence. But we do have convergence anyway. Then we do have quadratic convergence in some special situation, pretty broad. That if this guy, the generalized Hessian is positive definite in this case on the level set, and we have this standard relationship between parameters, then we claim that convergence rate is quadratic when h is given in such a form. It is maximum of affine function locally. If we have such a structure, which is not very narrow, it's good class of function, then we have convergence quadratic convergence rate. Then now let's go to KL, Kurdyka Lojasiewicz property, and then we can get better convergence and better rate of convergence. Then let me remind, I think in this conference, this notion was discussed in various talks. We have KL property as usual if we have convex continuous function psi such that its derivative is positive, and we have this condition in red, display condition in red. Okay, and then this is distance function, of course. Then what the theorem says in general that if we have iterative sequences of our algorithm and it generates the accumulation point at which KL property holds, then we have global convergence to a stationary point. So far, no rate, just we have global convergence. This result, which is pretty expected for any algorithm which we are doing here. In particular, it holds for our algorithm. Then there is some specified KL property or exponential KL property. How much that? Oh, I'm sorry. Very sorry for this. Okay. Anyway, in this case, when we have exponential rates, that we have some result about convergence rate, I would like to mention that this second, when C is from 0, 1 half, it's under more deep investigation, which we do with Yura Nesterov. Here, in this case, we may have not just linear convergence, but finite termination, or we may not have function at all which satisfies this condition, like in the case, for example, DC programming. Okay, then unfortunately, I don't have much time. I would like to mention that when we consider problem of sum, which also consider kind of composite minimization of sum when with plus f plus c is a plus. In this case, when f is good, c2 1, and psi is prox bounded, which is natural assumption, then we have actually we use what we call Asplund function. And Asplund's function, this is actually Asplund, well-known person in geometry of bounded space, and he introduced this function just as technique in his bounded space geometry proof. I am familiar with his paper and observed that it will work in our case. Using this Asplund function, we can get that all this problem with sum of two functions, when unconstrained, written in unconstrained form, but actually constrained, because psi may be extended real values, then we can reduce, using Asplund function, we can reduce our problem to the case of difference, and all these properties which are needed in our algorithm holds. Okay, we proceed with this one. Then another application is to problem of constraint optimization with geometric constraints. We minimize function f, which is good, but c may be just close set. And in this case, we proceed with so-called FBE, forward, backward envelope, which was introduced by Panos, Patrimas, and then, this function is better than the original one, but it gives the same value for the cost function. We proceed with this algorithm. This is direct implicit algorithm, and we have about the same property like for general case. Then applications are given for problem of binary classification in supervised machine learning and also in deep machine learning. Then application to biochemistry modeling. And what is interesting to observe? That for these problems, which are given in DC form, it means difference of convex, this algorithm can be fully realized and numerically provides better results than for DCA or for boosted DCA. That's, if somebody is interested, some of this talk can be found in my book, in particular the last chapter, but full amount can be found in this paper with Fran and Pedro. And here are some books which you can find all the machinery which I mentioned. Okay. Thank you very much, and sorry if I took more time.